In this video, we're going to look at 11.2 Day 1 on arcs and chords. We'll answer the essential question, how do you use properties of arcs and chords to solve problems? Let's start off with some vocab and concepts related to arcs and their measures. Central angles are angles whose vertex is the center of the circle. So in our picture here, the central angle is angle ACB. An arc is the unbroken part of a circle that's made up of 2 points called endpoints and all the points in between them. So in our picture here, arc AB is made up of endpoints A and B and then all the points along the circle in between there. You can find the measure of an arc by looking at the measure of its central angle. If we have a minor arc, we can name it with 2 letters, and the measure of a minor arc will always be between 0 degrees and 180 degrees. The measure of a minor arc is equal to the measure of its central angle. So you can see in the picture here that the central angle ACB is 50 degrees, and the measure of arc AB, which is a minor arc, is also 50 degrees. Now, a major arc is going to be named with 3 letters, and the measurement is going to be between 180 degrees and 360 degrees. You need 3 letters so you know which way to go around the circle. So ADB is a major arc. I'm starting at A, I'm heading toward D, and then I'm ending at B. And to find the measure of a major arc, you take 360 minus the measure of the minor arc. So here, 360 minus 50 would make that major arc there 310 degrees. A semicircle is neither a minor arc nor a major arc. A semicircle is just a half of a circle, and a semicircle is created if the endpoints of an arc lie on a diameter. So in our picture here, EG is a diameter. Let's add a point right here and call it C for the center point. Every semicircle is going to be equal to 180 degrees. So the measure of arc EFG is equal to 180 degrees. And then I forgot to fill in this part. This should say the word minus. So the measure of the major arc is 360 minus the measure of its central angle. And that should say central, not central. Let's try an example here. You've probably seen circle graphs before. Sometimes they're called pie charts. And this circle graph shows the types of grass planted in yards of one neighborhood. We want to find the measure of each arc. Notice that the values in the circle graph are given as percentages, and we're going to need to convert them to degrees. And in order to do that, the first thing we need to do is convert the percents to decimals. You can convert a percent to a decimal by moving it 2 decimal places to the left. So as an example, if we want to find the measure of arc GH, which is this arc right here, notice that that arc is associated with the portion of the circle that's 8% of the circle. So I'm going to begin by switching 8% to a decimal. We need to move the decimal place, which is right after the 8, 2 places to the left, and then fill that in with 0. So 8% is 0.08. Now the full circle is 360 degrees. We need 8% of that, so we're going to take 8%, 0.08, times 360 degrees. You can type that in your calculator, and it gives us 28.8 degrees. So the measure of arc, GH, is 28.8 degrees. That's also the measure of the central angle, angle GJH. Notice in the next problem, we're given 3 letters. This is a major arc. We're looking for the measure of KLF. Notice that that corresponds with this 65%, And as a decimal, 65%, we move it 2 spots to the left, is 0.65. So we need 0.65 times 360. You can put that into your calculator and you will end up with 234 degrees. For the try now, you can go ahead and find the measure of arc FG. Please pause your video now and give that one a try. When you do that, you should have ended up with 0.2 times 360, which is 72. So the measure of arc FG is 72 degrees. Next, we're going to talk about the arc addition postulate. This works just like the segment addition postulate and the angle addition postulate that we've learned about earlier in this course. The measure of an arc that is formed by two adjacent arcs is the sum of the measure of those two arcs. So as an example, in this picture, if I want the measure of arc ABC, we can break that up into the measure of arc AB plus the measure of arc BC. And that's going to be the measure of that full arc ABC. For example 2, we're going to use that property. It is often really helpful in these problems too to just fill in all the missing angles. It'll make it a little bit easier. And look for things like semicircles and vertical angles. I'm going to start by, solving problem A because all the numbers we need are given. The measure of arc LN, you can see that LN covers two arcs. It's the measure of LM plus the measure of MN. Together, LM plus MN makes up arc LN. Well, you can see that LM is 40 degrees and arc MN is 25 degrees. Using the arc addition postulate, we add those together and get 65 degrees. For part B, we're looking for the measure of arc JKL. Now, there's a lot of different ways that you can find these measures, but it does often help to fill in missing measurements right on the circle graph. So if I look like right here, these two angles are congruent. So if this angle here is 25 degrees, this angle there is also 25 degrees because vertical angles are congruent and those two angles are a pair of vertical angles. Now, another thing you can look for is you can look for semicircles. We know that semicircles are 180 degrees. And if I check out this diameter right here, the full semicircle here has to be 180. And if we subtract that 40 and 25 from that, you'll end up with 115. So this angle right here is 115 degrees. And then similarly, we could use a second diameter, this diameter right there, and figure out that this angle here is just 180 less 25, and that's 155 degrees. So now I have all the numbers filled in, and I can use any of these values to find the measures of the arcs. Let's go back to arc JKL. Using the arc addition postulate, we know that that's going to be equal to the measure of arc JK plus the measure of arc KL. And now that we've filled in all the missing values, you can see that that's just the 25 degrees plus the 115 degrees, and add those up, and that makes 140 degrees. For your try now, let's go ahead and look at the measure of arc JML. So make sure you go the same direction. So J to the M, then to the L. Maybe what you observe here is that you're going a semicircle like right here. So from J to M is 180 degrees. So arc JM plus arc ML. Well, JM is a semicircle, and we know that semicircles are 180 degrees. Add arc ML, which we can see is 40 degrees, and that gives us a measure of 220 degrees. The last example that we're going to look at here in the day one portion of lesson 11.2 involves congruent arcs, congruent chords, and congruent central angles and how they're all related. This theorem talks about congruent arcs. Within the same circle or two congruent circles, congruent arcs are arcs that have the same measure. So this theorem only applies if we stay in the same circle or we're in two congruent circles, meaning two circles that have the same length radius. Part one of this theorem states that congruent central angles have congruent chords. So in the picture here, if we know that the measure of BEA is congruent to the measure of CED, that's congruent central angles, well then they're making congruent chords. So chord BA is congruent to chord CD. For part two, congruent chords have congruent arcs. So this time we're given that BA is congruent to CD, and we're able to conclude that BA, arc BA, is congruent to arc CD. And then the last condition of this theorem tells us that congruent arcs have congruent central angles. So that would mean if we were given that arc AB or BA is congruent to arc CD, we would be able to make the conclusion that the central angles BEA and CED are congruent. These theorems also work if you take their converse, meaning if you go the opposite direction. So for example, the converse of condition number one is listed right here. Condition one states that if two central angles are congruent, then they have congruent chords. If we take the converse of that, it would say, well, congruent chords have congruent central angles. And the converse of the other theorems apply. I like to think of this theorem here as just basically if you have congruent arcs, you also have congruent chords and congruent central angles. Or if you have congruent chords, well then you have congruent arcs and congruent central angles. And if you have congruent central angles, you can make the conclusion that you have congruent arcs and congruent chords. So one of these congruent means the other two are also going to be congruent. So here is an example. For part A, we're given that circle A is congruent to circle J. If that was not given, we would not be able to apply that theorem that we just talked about. We're also given that angle GCD is congruent to angle NJM. And you can see that those are central angles. And looking at condition number one from the theorem we just filled out, congruent central angles produce congruent chords. So chord DG is going to be congruent to chord NM. And now we can do our substitution. Chord DG is this 14t minus 26. And chord NM is 5t plus 1. Let's go ahead and solve for the t. I'm going to move the 5t to this side by subtracting 5t. Then we want to move the minus 26 to the other side. Add 26. So I'm doing kind of two steps in one line here. 14t minus 5t is 9t. And 1 plus 26 is 27. Now just a quick divide by 9 gives us t equals 3. Well, the directions ask us to find NM. And now that we know t is 3, we can just plug 3 into this expression. So we'll take 5 times 3, add 1. That's 15 plus 1, so NM is equal to 16. Part B uses another condition of that theorem. This time, we're given that two chords are congruent, And we want to find the measure of arc WS. By condition number 2 of the theorem that we just defined, congruent chords produce congruent arcs. So that means that arc TV has to be congruent to arc WS. And again, we have expressions for those. So let's go ahead and do our substitution. TV is 9n minus 11, and WS is 7n plus 11. Now we can use our algebra skills here. I'm going to move the 7n to this side by subtracting 7n. And then I'm going to add 11 on both sides to clear that subtract 11. If you'd rather break this down and do those two things as separate steps, you can definitely do 2 separate lines. Either way, when you're all done solving, you should end up with n equals 11. Now that we know that n is 11, we can find the measure of the missing arc. So the measure of arc WS, I can see, is 7 times n, so 7 times 11 plus 11. And when you do that, that's 77 plus 11. So that means that the measure of arc WS is 88 degrees. For the try now, note that there might be a typo on your packet. So if this is not 7y minus 43 degrees, please cross it off and change it to 7y minus 43. This try now will use condition number 3 from the previous theorem. So go ahead and try this problem on your own. Please pause the video, and then when you hit play, the solution will be posted. And here is your solution. The measure of those 2 central angles have to be congruent because the circles are congruent and so are the arcs. This uses condition number 3. You can see I just set them equal to each other, solved for y and got 24. And then to get the measure of angle DEF, plug 24 into 7y minus 43, and you'll end up with 125 degrees. And that concludes the first portion of lesson 11.2. We'll do the last part of the lesson in the next video. Thanks for watching. Bye.